Hello everyone, welcome back. This is chapter 4.1. This is a discussion on rational functions and asymptotes, and I'm just going to begin on discussing first what a rational function even is. And here I say a rational function is just a function of the form polynomial function over another polynomial function. Usually we'll call the top one p of x and the bottom one q of x, but in any event, rational function anyways, just means that it's a polynomial function over another polynomial function. Here I say the domain of any rational function is just the set where its denominator is not zero, set of all x values such that its denominator is not zero. Usually you want to actually solve this inequality here. So solve exactly for what x cannot be equal to. We'll see that in these examples, of course. So let's just begin that. So here I asked to find the domain of each of these two rational functions. So all we're going to do is just set the bottom equal to 0 and solve. So let's see what happens. When you set this equal to 0, what we end up getting is that x is equal to 1. And since we want the denominator to not be 0, that means x cannot be equal to 1 as a consequence. So it's kind of like solving this inequality is just the same as solving the equality. So here the domain is just the set of all x values such that x cannot be equal to 1. There is actually a way of writing this in interval notation. It's a little funny though, I'll still show you, but it's like this. So you say you go from negative infinity to 1, open, because you don't touch 1 or else you'd be equal to 1. If it was closed, you'd be equal to. And then this union symbol means or the interval from 1 to infinity. So this interval here is the union of these two intervals, meaning that it's every number except for 1, because we go from negative infinity to 1, but you don't touch 1. You jump over 1 and then you go to infinity. It's kind of easier to see this set builder notation version of that domain, but there it is in interval notation in case you're curious. Here I think we have enough room for it, but let me just say this. To set this denominator equal to 0, first we have to do what? We have to factor the denominator. And the denominator, yes, it can be factored. It factors as the difference of squares, x minus 2 and x plus 2. And then you would set each of the factors equal to 0, and then you get x is equal to 2 or negative 2. So this would imply that x cannot be equal to 2 or negative 2 because these are really non-inequalities. They're not equal to. Okay, so our answer would just be the set of all x's such that x is not equal to 2 or negative 2. And I'll show you how to write that in interval notation. But before I get there, you may think, so this is not equal to. So before I get there, you may think for a second, well, this x minus 2 on the top cancels with it, and you're right, it does. That we'll talk a little bit more in the next screen, but for right now, let me just say this. Even if there's cancellation, it still would trigger a 0 denominator. So even though there's cancellation, it's still technically a 0 denominator. In fact, if you plug in a number directly, like let's say the one that would make it 0, like 2, before canceling you get 0 over 0, but after canceling you would get, let's see, those x minus 2's would cancel, so you'd get 1 over 2 plus 2 would be 1 over 4. But we're not plugging it into the canceled version, we're plugging it into the original. So even though it does cancel, we're looking at domains of the original function before cancellation, so that's the technicality there. So in reality, we don't care about canceling, we just care about straight up setting the denominator equal to 0 and excluding those from the domain. Now before I move on to the next screen though, I want to write this answer for the second part of this example in interval notation, and here's what it is. So we'd be going from negative infinity to one of these numbers. First we hit negative 2, then we go from negative 2 to 2, that's the next number in line, and then union 2 to infinity. Now I know these unions may be a little confusing for some of us because we haven't seen them before in this course, but let me just say that union just means or. So if a number is in the domain of this function, it is in one of these three. This interval or that interval or that interval. Regardless of which one it's in, notice it is not equal to negative 2 or 2. So the interval notation should still make sense. So the next important piece we need to talk about is what is called an asymptote. And the idea of asymptotical behavior can go actually beyond lines. But for right now, let's just talk about asymptotes as lines. So let me just say the following. An asymptote is a line that a curve will approach but never touch. And I say usually. So maybe this isn't the best way of describing it, but for our purposes of this section, it is the best way to think of it. So we'll see some cases where it will intersect the line, but the main idea is that it approaches the line as things go towards infinity, basically. And here are some 3 scenarios I want to touch on. So the first one is when you have a vertical asymptote. So imagine this vertical red line is not the curve, it's not even a part of the curve, but it is a vertical line that the curve will approach. In this case, it's in either direction, but it could be in the same direction or that direction as well. So either both towards positive infinity or towards negative infinity. In this case, it's towards each. Here, there is a horizontal asymptote. There's also a vertical asymptote if you look at this, but let me just talk about horizontal for a second, because you could have weird cases where they're like something like this, let's say. Here there's a horizontal asymptote here. So these lines will get closer and closer. This curve will get closer and closer to this line, but never touch the line. Now, one of the reasons why I say usually, you can kind of think of a case where it could weave in and out of the line, but it gets closer to the line. So imagine this. This is just an example of a horizontal case. You can imagine what it would look like for vertical as well. But notice what happens here. It seems to be getting closer and closer to the red line, but it doesn't exactly become the red line itself. So when I say never intersect, that's kind of incorrect. It really can intersect, actually, but it's never going to be exactly that line. It'll just approach that line as you go towards infinity. Okay, and a slant or oblique asymptote is one that is not vertical nor horizontal. It's just some line. So notice here, the curve will get closer and closer to the line out that way, and then closer this way as well. Also, it doesn't have to be the case for both directions, mainly just for one direction that really has to be the case. But usually it will be the case for both. And rational functions are functions that in particular have really nice cases of asymptotes that we'll actually classify right now. Before moving on though, I want to describe this in a more algebraic sense because this is very geometrical. So let me just say for vertical what's happening is that this line, this vertical line, is a line of the form, let's say x equals a. Any vertical line is of the form x equals a number. And what you can say actually is the following. So if the curve is a sketch, let's say it's a graph of a function f of x, then we can say that f of x will approach, so this arrow stands for approach, either plus or minus infinity as the x values approach a. So as x gets closer and closer to a, so if you imagine this is the x-axis, as x gets closer and closer to a from the right or left, the function will either approach positive infinity or negative infinity. In this case, it's both, but it could be only positive or only negative, as we've kind of discussed here. And here for horizontal, it's quite the opposite. So for horizontal, what will happen here is f of x will actually not approach infinity, but f of x, remember f of x is the y value. The y values will approach this line here. And let's say this line is y equals b. So what happens here is f of x will approach, not equals, but approach b as either x will approach positive or negative infinity. So in other words, as x gets larger and larger and approaches the right, so again, if you imagine, let's say this is the x-axis here, and I drew a y-axis, which we don't really need, but let's imagine x is getting closer and closer to positive infinity. Notice the curve is getting closer and closer to b, so the y values of the curve are getting closer to b. Similarly, as it goes towards negative infinity, it also gets closer to b as well. So the y values of the graph will get closer to b. And for slant or oblique asymptotes, well, here's what we can say. We can say that if this has the equation y equals mx plus b, because any line that's not vertical or horizontal can be written like this, well, then we can say what you think. F of x will approach, keep writing equals, I mean approach, y equals mx plus b. We can just say mx plus b. That's fine. As x gets closer towards positive or negative infinity. Right. So now we'll take a look at the classifications I was talking about just now. So these are the classifications I was talking about. There's a lot to discuss, so let's just get right to it. I say here that for f of x being equal to p of x over q of x, so some rational function, the following holds. So there's three things to talk about. First thing is that if p of x and q of x have any like factor, so that means you can cancel the like factors, kind of like we saw in the second example. Let's say the factor is x minus a, then the graph of f of x has a hole at x equals a. So it's just a point that's excluded that we indicate with an open circle. So we'll probably do an example of that later, but that's just one case to keep in mind. That honestly is very rare, but I wanted to include that because it's something people kind of forget about. So that can happen. But the more important ones are 2 and 3. So 2 says after cancellation of any like factors, so basically assuming there are no like factors of p and q, then the graph of f of x has vertical asymptotes, which I'll now call VA, at the zeros of the denominator. So when the denominator is equal to 0, basically the numbers we exclude from the domain, those are the vertical asymptotes, provided there's no cancellation. So back to that second example, the x minus 2 is cancelled, so there's only one vertical asymptote. If there was no cancellation, then there wouldn't be a hole, but now there would be 2 vertical asymptotes. Okay. 3 says for horizontal asymptotes of x, there are 3 cases. So there's 3 cases for horizontal asymptotes. Vertical asymptotes are pretty easy to find. Do any cancellation first, then set the remaining zeros or the remaining factors equal to 0 and solve for that. But for the horizontal asymptotes, there are 3 cases, and it depends on the degree of the numerator and denominator. So here, if the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is y equals 0. So here, horizontal asymptote, I'm referring to as h of a, just to include that there. So y equals 0 if the denominator is smaller than the top, as far as the numerator is smaller than the top, as far as degree is concerned anyways. If the degrees are equal, then the horizontal asymptote is y is equal to LC, stands for leading coefficient. So remember, lead coefficient or leading coefficient is just the number in front of the largest power of x. So you just look at the quotient of the leading coefficients of the polynomials in that order, top and bottom, and that will be the horizontal asymptote. And here, finally, if the degree of the top is larger than the degree of the bottom, then there is no horizontal asymptote. So for horizontal asymptotes, there's only one. Opposed to vertical asymptotes, there could be many. And that's really all I want to say. Now we'll take a look at some examples. All right, so here are the examples I want to speak of. And let's just get right to it, shall we? We have to follow the procedures that I showed you basically from the previous screen. And we're going to start by factoring any like factors. With the first 2 we can factor, the bottom one we'll have to factor. Now, let's just start obviously with the first one. So here to find vertical asymptotes, what are we doing? We're setting the denominator equal to 0. When x squared is equal to 0, we just get x is equal to 0. So there's our vertical asymptote. What about horizontal asymptote? There were 3 cases. 3 cases. What were the 3 cases? Either the degree of the top is smaller than the bottom, equal to, or bigger than. Here, the degree of the top is 0 because there's no power of x. The largest power of x here is 0. Power of x on the bottom is 2. So just to write things specifically here, let me just say that degree of the numerator, let's just say 4, is equal to 0, whereas the degree of the denominator, which is x squared, is equal to 2. So that's what I mean by highest power of x. If there's no power of x, it's a constant, so its degree is taken to be 0. And here, the degree of the top is less than the degree of the bottom, so that was the first case. So let me just say here, this was case 1. And what did case 1 say? Case 1 said that y equals 0 is the horizontal asymptote. And that's it. Perfect, so we're going to follow that procedure. So now for this one here, for number 2, we're asked to find, again, vertical asymptote and horizontal asymptotes. So vertical asymptote, you just set the denominator is equal to 0, provided there's no cancellation. Even though it may kind of look like there's cancellation, there's no cancellation. 5 plus x and 5 minus x actually have no common factor, even though they look very similar. If there was a negative in front of this 5, you can pull out the negative, and then it'd be 5 plus x over 5 plus x with a negative. But there is no negative in front of that 5, so there's no cancellation. So the vertical asymptote here is just when the bottom is equal to 0. So if you set this equal to 0 and add x to the other side, you get x is equal to 5 for the vertical asymptote. For the horizontal asymptote, well, the degree of the top is 1 because the highest power of x is 1. Same with the bottom. So their degrees are the same. So this is actually case 2. And what does case 2 say to do? Case 2 says that the horizontal asymptote is y equals the leading coefficient of the top divided by the leading coefficient of the bottom. So here, the LC of the top, so let me write a 5 plus x, is just the number in front of the highest power of x, which is 1. And the leading coefficient of 5 minus x then would be -1, because the number in front, the coefficient of, rather, the largest power of x of 5 minus x is a -1, because it's -1 times x. So the answer here is just, well, leading coefficient at the top divided by leading coefficient at the bottom. So it's 1 over -1. That's just y equals -1. It's a little tricky to see, but after some practice, you'll get the hang of it. Now, finally here, vertical asymptotes and horizontal asymptotes. This is definitely the trickier of the bunch because there's factoring to be done. So let's factor, shall we? Can we factor? Well, the top can be factored as what? What two things multiply to -4 and add to -3? And of course it's 4 and 1. In order for them to add to -3, it has to be -4 and +1, like this. And you can check that when you FOIL this out, you indeed get back this. The denominator is trickier to see, but just so I don't waste too much time, let me just tell you that it is indeed this. And what I would do normally here is I do the following. I know it has to be x and 2x to multiply to 2x squared. I know it has to be 1 and 1 to multiply to 1. So I don't know the signs. So if I guess that the signs are like this so that these would cancel, which is kind of what I'm assuming will happen, then we can check by foiling, and when you FOIL this, you indeed get that back, the bottom. If it wasn't the case, then the signs would be swapped, and if that doesn't work, then it can't actually be factored, which is a possibility. So here, there's cancellation. So instead of 2 vertical asymptotes, there's only 1, because this is what remains after cancellation. Remember, vertical asymptotes, we only set the denominator of what hasn't been cancelled already equal to 0. When you set this equal to 0, you add 1, divide by 2, you get x is equal to +1/2. Perfect. For horizontal asymptotes, the degrees are the same. They're both 2. So it's just the number in front divided by the number in front. So it's 1 over 2. In other words, this is also case 2. Something else I want to say here is that there's a hole. Even though they didn't ask us to find the hole, I'll tell you what the hole is. The hole happens at x equals what? At x equals whatever canceled. So if you set whatever canceled equal to 0, you get x is equal to -1. So the hole isn't the point x equals -1, but if you go to the point of the curve at x equals -1, you'll see that point where we'll make that hole. I do want to show the graphs of these, so I'm going to erase some of this stuff. I'll leave the examples and I'll just show you the graphs and we can kind of compare. I'll leave the answers so we can compare that as well. Right, great. So this is what we concluded, and let's try to see if we can figure out what the graphs are. Now, this section doesn't really focus on the graphs too much. It's funny because it focuses on asymptotes and domain, which have some relationship with the graph, definitely have a lot of relationships with the graph. But it doesn't discuss the graphs. In fact, 4.2 discusses more of the graphs. But the way I'm handling this section will make 4.2 a lot easier. So let's see. So the vertical asymptote is going to be x equals 0. X equals 0 isn't the x-axis, by the way. Just so we have that straight. X equals 0, remember, x equals a number is a vertical line. So the y-axis is actually the line x equals 0. Similarly, the x-axis is actually the line with equation y equals 0, just like that. So that is a little counterintuitive and people often get messed up there. Don't get messed up there. So just to emphasize on that, let me draw the vertical asymptote here in red at the y-axis, and the horizontal asymptote here in red, which is the x-axis. Okay, good. Now, as it turns out, because it's x squared only on the bottom, when you plug in negatives or positives, you still get only a positive number. So the graph will actually look something like this, believe it or not. And you can check this with your graphing calculator or an online graphing calculator of your choice, but the graph will indeed be something like this. I'm not plotting specific points. I'm just giving you an idea of the shape with the asymptotes included. So we can see it approaches this vertical asymptote and this horizontal asymptote as x goes towards positive infinity and negative infinity. Good. So what about number 2? Well, number 2, the lines we have to draw now are x equals 5, which is here. It's a vertical line. That's our vertical asymptote. And y equals -1 is down here. That's our horizontal asymptote. Now, it's a little funny to kind of see what happens as far as where the graph is located. But what you can do actually is you can just pick different numbers in these quadrants of, I guess, this grid you get created by the intersection of the asymptotes. But like, just for instance, if you plug in 0, 0, if you plug in 0, 0 for x, well, if you plug in 0 for x to see what y is, I should say, you get 5/5 for y, so that's +1. So at 0, y is going to be +1, which tells me that the graph is going to be on this side, and we'll do something like this. So it'll approach the horizontal asymptote and the vertical asymptote as you go towards x equals 5. And because the degrees at top and bottom are both odd, there's no weird thing happening here where it's all positive. In fact, if you were to plug in a number off to the right, for sure you get a number below -1. And just to show you, if you plug in, let's say, a 6, well, plugging 6 in here will give you 11 on top, but 5 minus 6 is -1 on the bottom, so that's 11 over -1 is -11. It's going to be way down here. So the graph will look something like this, of course not to scale. So this is the kind of weird shape we get like that. And notice it is a function because it passes the vertical line test, which is why I know to the right, well, I guess to the right and to the left is what I really mean to say. We see if it's above this line or below this line. So there's some detail there, but you can work that out on your own. And lastly, for this one, if we plot, well, before we plot the whole, let's graph the horizontal and vertical lines. So the vertical line is at 1/2, so let's say that's right here. And the horizontal one is also at y equals 1/2. Good. And there is a hole at -1. Now, if you were to plug in, let's say 0, which is an easy one to plug in, you get -4 over -1, which is +4. So that means it's going to be over here somewhere, +4. So if you plug in +4, well, that's at x equals 0. So when x is equal to 0, y is equal to +4, so it will look something like this. Kind of like what we got over here. And actually, similarly, it'll be below. I'm not going to plug in another point, but you can if you want to do it. It's going to be a lot of work to show. But if you plug in a point, an x value to the right of x equals 1/2, you'll indeed get something below this line y equals 1/2. So that tells me that it's below, not above. Also, I'm missing out the hole. The hole is at -1. So if you go to x equals -1 and project to the curve, just take that point out and draw an open circle there. Now, one important note is that the hole isn't really something that we strive for when graphing. In fact, if you use a graphing calculator or even a graphing utility online, very rarely do they actually spot the holes because it's an infinitesimal in the sense that it's just one point. It has 0 dimension basically. So it's hard for the graphing utility to emphasize on that point. So you can check it out, but you'll see what I mean when you graph these things. So there we go. That concludes 4.1. I'll see you in the next video for 4.2. I think it's going to be a little short because it'll mainly be examples like we just saw here, but it'll still be more to reinforce our knowledge. So thanks for watching. I'll see you in the next videos.